Welcome to the sixth week. This week and the next week, we will be studying our basic measures of information and we'll be reviewing their properties. And some of these properties you have already seen in this course before, but we never gave formal proofs of these probabilities, and this is what we are going to do now. And we will define these things a little bit more carefully. We will cover chain rule, we will cover data processing inequalities, Fano's inequality, Pinsker's inequality, and many other relations between these measures of information. This week, I will write the lecture live rather than using previously written notes. And the reason is that this part of the course will be rather proof heavy and a bit technical. I'll give typed notes separately, but the derivations I'll try to do slowly by writing live. So I hope you enjoy these lectures, and let's continue with the videos for this week. In this first lecture, I will start by reviewing all the different measures of information that we have seen so far. These are the main characters of this course. We will visit them again and again. So the first quantity that we saw was Shannon entropy, and we defined Shannon entropy for discrete random variables. So we considered this PMFP on X, and X is a finite set. It need not be finite, but it's a discrete set. So it can be countably. Its support can be countably infinite. For example, it can be a set of natural numbers. And for this for this P, we have defined Shannon entropy, H of P, by this formula: summation over X, Px log 1 by Px. A quick word on notation. So in this part of the course, in this week's at least, I'll use capital P. I'll try to be consistent with my notation, but more or less I'll use capital P to denote the distribution, and small p to denote the PMF. Okay, so this is the PMF, or for the case of continuous random variables, the density of P. Okay, so small for density, PMF for density, and capital for distribution. So this notation, using this notation, entropy is summation over X, Px log 1 over Px. Okay, so that's entropy for us. The second quantity that we have seen is different variants of this entropy. We saw joint and conditional entropies. The first one is an obvious extension of this definition of entropy. One remark on notation again. So this h of p, entropy, most of the time we want to see it as a function of the distribution, but sometimes it is convenient also to write h of x for a random variable x with distribution p, and this is the same as h of p. Okay, so Shannon entropy. The other variant of Shannon entropy that we have seen is joint entropy, which we can define for a pair of random variables. So suppose you have this x comma y, two random variables with joint distribution pxy, then you can talk about their joint entropy. Okay, this is defined in the same way, but the summation will be over both xy, and we again abbreviate it as h of x comma y sometimes. So this is the joint entropy of x and y. Joint entropy of x and y. Somewhat related but different is this notion of conditional entropy, which we denote by pxy given py, or h of xy, x given y for short. This guy here is defined as, this is my notation for defined as, summation over xy pxy log of 1 by the conditional probability. Okay, I'll try to remember my own notation, but if I make mistake, I hope you can draw the connections. Okay, so this is conditional entropy. This is, as you can see, this is equal to the expected value of h of p x given y, and this expectation is over y, the conditioning variable. This expectation is over y. So right. So this is the residual randomness in x given y. This is the total joint randomness of x and y, and this hx is the randomness in x, uncertainty in x, randomness in x. Okay. Entropy, conditional entropy, joint entropy. The other quantities we have seen so far is the third quantity we have seen so far is the mutual information. Okay, so this mutual information captures the information that x has about y. So we denote it by I of xy. This is for a fixed joint distribution of xy, and we define it as the change in uncertainty. The reduction in uncertainty is information. So h of x minus h of x given y. That's mutual information for us. And we saw several equivalent expressions for this quantity in the last week. We'll come to those expressions. Actually, those expressions are something that you should remember and quickly derive. But I would like to introduce a notation here. If you fix the distribution of x as p and the distribution of y given x as this channel w, then this mutual information is a function of p and this channel w. Okay, so input distribution and channel the channel description. Okay, the conditional probability. And I would we would basically want to view mutual information as a function of these two quantities, this pairs. Sometimes we'll fix the channel and view mutual information as a function of p, or we'll fix p and view mutual information as the function of channels. So that's the other quantity we have seen in this course, mutual information. Next quantity that I want to recall is this notion of distance, the Kullback-Leibler divergence. Okay. So what is KL divergence? It is, so suppose you are given two distributions, P and F, P and Q, on the same alphabet X. For now, assume both are discrete distributions. So for these guys, we can define dpq as it can be defined as summation over x, px log px log px by qx, where this qx is the PMF for q. And this definition is valid if the support of P is contained in the support of Q. So what is the support of P? This guy is a set of those point x for which Px is greater than 0. Okay? So it need not be the entire x. It can be a subset of x. So those point x in x. So x in this set x. So what does this relation mean? It means that if q is 0, p must be 0. So you can define px by qx. So this is the definition. If support of p is not contained in support of q, then we simply define Kullback-Leibler divergence to be infinity, because you have a 1 by 0 form. Okay. One thing I would like to note here is that Kullback-Leibler divergence can be related to entropy. The Kullback-Leibler divergence between P and a uniform distribution. So this is a uniform distribution on Q. Uniform distribution on X. Okay. So this thing is exactly equal to log of cardinality of x minus h of p. Okay, so this is some relation which you can check very easily. Also, the divergence between pxy and pxpy, that's something we saw last week, is the same as mutual information. So this divergence is sort of a very general quantity which recovers many of the notions of uh, measures of information as special cases. So this particular relation also makes sense. Entropy is the measure of randomness. What is the most random or most uncertain random variable? It's a uniform random variable. Therefore, a measure of randomness is how far your distribution is from uniform, and that's what this measure gives you. So this brings out entropy. This brings out a simpler notion of measure of randomness. Okay, so Kullback-Leibler divergence. The other kind of distance that we have seen so far is this total variation distance. Total variation distance, and this total variation distance dpq is defined as half into summation over x. X is from this alphabet x, but I'm just omitting that part. Px minus qx. Okay, that's, you can think of that as a definition. We have seen other equivalent expression for this total variation distance. So a very important one is this one. dpq is sup over a subsets of the set x, p of a minus q of a. Okay, in this form, sometimes this is called the variational distance. Okay, this guy has many names. Total variation distance is called variational distance. It is also called statistical distance sometimes. And well, in some relation to a more formal notion, this is also the L1 distance between these PMFs, which can be viewed as vectors of finite dimension if x is finite. Okay. Okay. So these are the 5 main characters: entropy, joint entropy, mutual information, Kullback-Leibler divergence, and total variation distance. All right. So let me. So one thing I want to notice before I move forward is that total variation distance and Kullback-Leibler divergence both can be expressed in a common way. So here is that common way. So dpq is equal to, you can verify this, expected value over q. There are 2 distributions, so I have to specify which distributions am I taking expectation over. P of x by q of x log of p of x by q of x. This p, remember this p and q are PMFs of p and q. So it's this function. Okay, so think of this function as fx. I should call it something else. Maybe fy is y log y, and so we just compute. So this guy here is simply expected value over q of f of px by qx. Okay. Interestingly, even the total variation distance can be expressed in a similar form. So total variation distance dpq is expected value over q. You can check this, mod of px by qx minus 1. Well, there's a normalization by half. Okay. So once again, if I define this f, so this, maybe I should call this function f1, and so now I can define f2 of y as half of mod y minus 1. So once again, this guy here is eq of f2 of px by qx. So both these distances can be expressed in this form, some function of px by qx. In fact, both f1 and f2 have a sort of a similar geometry. Both of them are so-called convex functions. We'll see that later. But these expressions are very interesting. So till now we have defined everything for discrete distributions, distributions where PMF captured a density. But using these expressions, we can easily extend them to beyond discrete distributions. So how do we do that? So let's see. Okay. So these expressions here can be used to go beyond discrete distributions. Well, how do we do that? So here is one way of doing it. So dpq and total variation distance for continuous distributions. How do you define it for continuous distributions? So all you need to do is take these formulae here and replace this ratio fx by q, f by q, with ratio of densities. That's all you have to do. So px by qx, both these are defined in terms of px by qx. You replace it with f place it with, so this was the ratio of PMF here, ratio of densities. Okay, so we use the same notation actually. So P is the density of X now, and Q is the density of Q. So these densities exist for continuous distribution. Just replace this guy with these densities, and you'll get the same definitions. In fact, this notion is very general. The fact is that what you see in more general probability theory is the ability to define density of P with respect to Q. Currently, this densities P and Q are both with respect to the length measure, the Lebesgue measure, but you can also describe more generally. So for any P and Q, we can use the density of P with respect to Q. I have not defined this term to replace px by qx. So then this definition will be extended to more general distribution. So what are even more general distribution? Mixed distribution, for example, are more general distribution. So these densities need not exist to define this. You can think of PMF as density with respect to counting measure. How many? What's the probability per count? This is the probability per length. Similarly, you can define probability per another probability. And in fact, this guy has a name. If you have seen that name, you will quickly recognize what I'm talking about. This called the Radon-Nikodym derivative. Okay, and it's denoted by dp by dq of x. So for those of you who are aware of this theory, I just wanted to point out that these definitions can be extended to any arbitrary measures. And for densities, for distributions with densities and PMFs, we just took ratio of densities and ratio of PMFs. But in general, you can have Radon-Nikodym derivative. So for this more general measures, dpq will be given by the expected value with respect to q of f1, that f1 function that we just defined, dp by dq. So this is a function, this is the random variable here. Okay, and similarly dpq, the total variation distance, is defined as expected value over q, f2 of dp by dq. So you are not expected to know this theory. I just wanted to quickly point out to the probabilists who are taking this course. All right, so all our definitions are in place. Um, so, so one thing now I wanted to point out before closing this lecture is you've seen all these different notions now. This, yeah, let me give you a bird's eye view of everything. So we've seen all these notions now, measures of information, this 5 measures of information, and we saw this general formula which so I'm calling them measures of information as general. I'm also calling this distance as measures of information, and we did motivate why these distances can be thought of as measures of information. And they, since most of these measures, all of these measures actually can be related to divergences, you can extend them to more general distributions. That's what I've shown here. But this is a bit of a delicate issue. It requires some more careful theory, which is not the goal of this course. So I'm not dwelling too much on it. But you can take a look, and you can at least map those more general definitions to a simple definitions. So one thing now I want to conclude with is that for each of these measures of information, there is a corresponding conditional equivalent. Okay, so I'll call it the conditional. I'll call it the conditional measures of information. So we have already seen this for entropy. So just for entropy, we have conditional entropy, and similarly for mutual information we can define conditional mutual information. So we saw this mutual information. We can also define this conditional mutual information of xy given a third random variable z, and this is defined as the expected value over z of the mutual information with input distribution condition on z, and the channel itself being the distribution of y given xz. So it's a very common recipe for all these definitions. So this guy also is the expected value over y of conditional probability. So basically take the conditional joint distribution, that's what mutual information depends on, and take average over z. That's how we define all conditional quantities. Similarly, we can define this conditional divergence. So what is the conditional divergence of x given y? So so think of two distributions px and qx. This is our divergence. It has a conditional variant. So the conditional divergence between x and y, between p and q, two different distributions given y, is denoted by this thing. And you also have to define the averaging distribution. I'm just taking it as py. Okay. And so this is also equal to, defined as of divergence between px given y and qx given y. Right. So these are the conditional variants of each of these quantities. Okay. So conditional variants of our measures of information. Okay, so conditional entropy, conditional mutual information, and conditional divergence. All right, so this is all I wanted to review. We have seen all the definitions now, and we have seen their conditional variant. And just as I've been saying, they can be extended to more general distributions than just discrete distributions. In the next lecture, we will start by showing the first property of all these measures, namely the chain roots. So see you in the next lecture.